Okay guys, so this is going to be our video of rotational kinetic energy and moment of inertia. We're going to cover a few different things in this set of notes. When we're talking about kinetic rotational energy, it's going to be the energy that something has while it's rolling. In this formula, rotational kinetic energy is equal to 1/2 I omega squared, where I is the moment of inertia and omega is your angular velocity in radians per second. Okay, so you need to make sure you're in radians per second. Let's talk a second about what moment of inertia is. Moment of inertia is different for every shape, okay? So like in this table down here, we have different shapes going about different axes. We're going to be using these three moment of inertias for our practice problems. We have a hoop, and we have a cylinder, and then we have a sphere, okay? Just keep in mind, you can change your moment of inertia by changing the shape. If I extend my arms while I'm rotating, I'm going to rotate slower. If I pull them in, I'm going to rotate faster. And we'll take a look at that in just a second when we're talking about conservation of angular momentum. Okay, so our first example problem, it says calculate the rotational kinetic energy of an ice skater who has a moment of inertia of 0.5 kilogram meter squared and an angular velocity of 15 radians per second. So we say 1/2, your I is 0.5, and your omega is 15. I'm gonna square it. So 225 times 0.5, divide that by 2. And she's going to have 56.25 joules of energy. Okay, so this will put you in joules. Okay, just like kinetic energy and potential energy were before. Okay, so we've already talked about this. So you need to make sure you pay attention to the shape that we're dealing with. We're not going to get too complicated. When you go to classes like statics or dynamics, in college, if you're going through engineering, mechanical, civil, or chemical, you have to take those classes. These things come from calculus. These formulas come from calculus, and integration. So don't worry about it. We're not having to deal with it right now. Okay, so just use these formulas. Okay, next example problem. So it says a solid sphere of radius 0.3 meters has a mass of 2 kilograms and rolls down a ramp without slipping. Okay, the without slipping part's important. If the ramp is inclined at 30 degrees and starts from a height of 4 meters, what is the velocity of the sphere at the bottom of the ramp? Okay, some of this information we don't really need, so I'm going to draw myself a picture. Okay, so draw ourselves a picture. It's at a height of 4 meters. Angle of incline is 30 degrees. And we have a sphere, okay? The mass is 2 kilograms. And its radius is 0.3 meters. Okay, so what we're going to do on this type of question is we're going to look at the types of energies as we did before. Say we did this before. We dealt with a block sliding down an incline, or we looked at someone skiing down a slope. So we're going to be dealing with something rolling, so it's going to be a little bit different. Okay, so the energy at the top is going to be potential energy. It's not rotating. As it rolls down the ramp and all the way at the bottom, it's going to be kinetic energy, linear kinetic energy, and since it's rolling down, you're going to have rotational kinetic energy. Okay, so we're going to add that element in there. So same formula from before. Potential energy is mgh. Kinetic energy is 1/2 mv squared. And your rotational kinetic energy is 1/2 I omega squared. Okay, so it's always like that. Now, let's deal with this I and this omega. So we're dealing with a sphere. So mgh is equal to 1/2 mv squared plus 2/5 mr squared. Now watch this. I'm looking for the velocity. So I'm looking for the linear velocity as I go down. So we had this form of V is equal to omega r, correct? Well, if I solve for omega, we get V over r. Okay, our linear velocity over r. So that's what we're going to put right here. And we're going to go ahead and square it out. Okay. So once again, I substituted my I as 2/5 mr squared because it's a sphere. I get that from the front. Omega is equal to V over R, and so I'm going to go ahead and square it out. Now a whole bunch of stuff should cancel. So the R squareds should cancel. Okay, the 2's cancel right here. And so I'm left with mgh is equal to 1/2 mv squared plus 1/5 mv squared. Okay, so if we're going to combine our like terms, we can cancel the m's, the masses don't matter. And we're going to plug in. Our height is 4. Okay, 1/2 plus 1/5 is going to be 7/10, I believe. Yeah, 7/10 v squared. And I can solve for v from there. So 9.8 times 4. Okay, we're going to divide by 7/10, use parentheses. So you get 56, and then we're square root it. So we get 7.48 meters per second. Now you're going to have, I think, 3 of those on your homework questions. So make sure we do those and know how to do those, because this does show up on UIL, this type of question a lot. So Carlos and whoever else is doing UIL science, make sure you know how to do it. Okay, last thing we're going to talk about in this note section is going to be conservation of angular momentum. Okay, so conservation of angular momentum, whatever momentum I have from the beginning, I end with, okay? It doesn't go away. Now you have something called the parallel axis theorem. So what that says is I'm initially spinning, okay? I have some sort of moment of inertia before I start changing my arms or my legs, you know, to spin faster or slower, okay? So I'll show you how to do that in just a second. So a skater has a moment of inertia of 100 kilogram meter squared when his arms are outstretched, and a moment of inertia of 75 kilogram meter squared when his arms are tucked in close to his chest. If he starts to spin at an angular speed of 2 revolutions per second with his arms outstretched, what is his angular speed when they're tucked in? Okay, so we're going to use I initial, omega initial is equal to I final, omega final. So your I initial is going to be 100, and your initial speed is going to be 2 revolutions per second. Now let's go ahead and convert that. We need to be in radians per second for these types of questions. So 1 revolution has 2 pi radians. Okay. So that puts me in radians per second. So pi times 2, 12.57. Okay. So you get 12.57. Your final moment of inertia is going to be 75. Okay. It's after he brings his arms in. Okay, so we can solve for omega final. So omega final comes out to be, so we're going to do 100 times 12.57 divided by 75, 16.76. Radians per second. Okay, So if you decrease the moment of inertia, you should spin faster. Okay, so that's why ice skaters spin so much faster when they bring their legs in. And you can change it by height. You can change it by, your radius of your arms. There's all different things that can change your moment of inertia that we're going to look at. Okay, a girl is on a merry-go-round that is spinning at an angular speed of 20 radians per second. The girl has a mass of 20 kilograms, and the merry-go-round has a mass of 250 kilograms. She is at a position of r is equal to 1.5 meters and runs to the edge to yell at her friend at a radius of 5 meters. If the moment of inertia for the system is originally 100 kilogram meters squared, what is the new angular velocity of the system when the girl moves to the edge? Okay, so what I would say is we're going to do parallel axis theorem on this one because we're moving from one location to another location. Okay, so our I initial. Okay, so our I initial, the moment of inertia for the system is originally 100 kilogram meters squared. Okay, now she is, so that's like what it should be if, see, this is kind of confusing because how it's worded. Okay, so we're going to treat this as if she's at a radius of 0. So she's at the center. And so if we were just going to be rotating with her at the very center of the merry-go-round, so our I initial is going to be 100 kilogram meter squared. Okay, we got to find our I final. Now, when she moves out to the edge of the merry-go-round, it's going to change her moment of inertia. It's going to change the system's moment of inertia. Okay, so the ICOM is what the moment of inertia is originally. So it's 100. So what is moving? Well, the girl's moving, so her mass is going to be 20. And what distance does she move? Well, she moves out a radius of 5 meters. Okay, so we're going to square that. So our new moment of inertia is 25 times 20 plus 100 is 600. See, if it was worded differently, if it said, okay, her moment of inertia, if her moment of inertia at a radius of 1.5 was 100, what's the new moment of inertia? She would have only traveled, what, 3.5 meters? So we would put 3.5 meters right there. But I think the way it was supposed to have been written is saying that the system just spinning with her at a radius of 0 should have been 100. That's the way I interpreted it. So anyways, just go with the flow on that. So we're going to use our conservation of angular momentum. Okay, so our initial moment of inertia is 100. It's initially spinning at a radius of 20 radians per second. Okay, your final moment of inertia is 600. And your omega final is what we're looking for. Okay, so 100 times 20 divided by 600 is going to be 3.33 radians per second. Okay, so if you extend your radius, you're going to be going slower. So you know, if you ever want to try this, you know, one day when you're bored at the park, you know, see if the merry-go-round goes slower when you're going around it and you go to the edge, okay? It might not instantly happen, but you should go slower if you go to the edge. If you go more towards the center, it should go faster, okay? So this has been your notes over rotational kinetic energy and moment of inertia. Thanks, and have a good day.